I would advise you to, as you're watching these, to kind of pause when we're at a point where I'm about to do something. If you think you know what I'm going to do, try to do it yourself. Try to predict. The more you do that, the more sense it'll all make to you when we're done. So I just want to review a little bit first from what we were doing last week. We were looking at power series. We talked about how you can have a power series represent a function. And we started from the fact that we know the geometric series. We have a convergence formula for it, right? So if you look at the geometric series, you've got the summation of r to the n, right? R is your base. It's the common ratio from one term to the next. And so when you look at that geometric series, we know that this summation is equal to 1 over 1 minus r. And also we can have a constant multiple, right? We can have a constant multiple on there like a, we've called it before, and then you just have a over 1 minus r. So that gives you this kind of, for a function, f of x, if you look at the function f of x equals 1 over 1 minus x, we can actually kind of go backwards now. Instead of taking the series and writing what it converges to, we can take this function and say, hey, here's a series, an infinite series that is equal to that function, right? Which means that you can actually approximate the function by using several terms of this series, right? If you start with like 1 and then x squared, as the powers go up on x, remember this only works for values of x that are less than 1 in magnitude. So as the power goes up on x, those terms get smaller and smaller and smaller. So you could stop at any point and you've actually got an approximation for the function itself, right? Now that might not seem very useful for 1 over 1 minus x because we can, we're pretty good at evaluating 1 over 1 minus x, but there's a lot of functions that this is going to help us with. So we saw last week that we can use that to find some other functions. So we took that geometric series convergence formula and we used it to create a power series. We could plug in some different expressions for x, right? So if we plug negative x cubed in for x, right? Then you have 1 over 1 minus negative x cubed, or 1 over 1 plus x cubed. And in that case, the series, when you plug it in, you plug in negative x cubed for all of the x's that we had up here. We're going to plug in negative x cubed, and you get this alternating series, right? Because when you plug negative x cubed in for x, you get negative x cubed. But when you plug it in for x squared, when you square the negative x cubed, you get positive x to the 6th, and then negative x to the 9th, and so on. You get this general term, and it just keeps going. Okay, again, this one only works for magnitudes less than 1, because if you need x cubed, or negative x cubed, to have an absolute value less than 1, then that's the same solution for x. X is going to have to be between negative 1 and 1 as well. But you can really do that for any function of x. If you plug some other power of x, for example, into that formula, you just have to be careful how you plug it in. Plug it in for all the x's in our main power series above there, and it should come out right. So we did that. We found we can plug in some different expressions for r there. But then we could also do some calculus, right? We could take the derivative of the function. We didn't do this one in class, but we actually did integrals. But if you take the derivative of the starting function here, 1 over 1 minus x, go ahead and do that. And you should see that you get 1 over 1 minus x quantity squared, right? You're going to get a negative 1 from the power rule, but then you're going to get another negative 1 from the chain rule. They'll cancel out. And then what we can do is you can actually take the derivative of both sides of this equation here, right? So you take the derivative over here, and you end up with this. Okay, so we have a power series now for 1 over 1 minus x quantity squared. And of course we could do it again and again if we wanted to. We could just keep going. And in addition to that, you can also take the integral. Now we talked about this in class, And there was one part I left out. I left out plus c, the constant of integration. Because I think we did it on this function, actually. We might have done it on 1 over 1 plus x squared for the inverse tangent of x. But it is important to consider it. In this case, well, you'll see what happens with the plus c. Sometimes it ends up, maybe the c is 0 and it doesn't really matter. But you should consider it. So here's the deal. If we wanted to integrate 1 over 1 plus x, obviously we get the natural log of 1 plus x plus c. And so if we want the series for natural log of 1 plus x, we can just kind of move that c over to the other side and take the antiderivative, and this is what you get, right? And it continues. I should probably have another plus dot 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 at the end there. So the natural log of 1 plus x is equal to, again, you take the antiderivative of 1 and you get x, right? Of negative x, you get negative x squared over 2, and so on. And then that plus c, I just added c to the other side, subtracted it, but remember it's just a different c then. And there we go. You can even do that with the, you can do the power rule on the nth degree term. And if you do that, if you do the power rule on the nth degree term, you're going to get negative x to the n plus 1 over n plus 1, which the x to the n plus 1 over n plus 1 doesn't really matter. If you make it x to the n over x to the n, it still works. It's just a different n, right? That's calibrated a little differently. And then we just need to make sure that the alternating piece is properly calibrated, right? So if you look at negative 1 to the n plus 1, the way we've got it down here is that when n is odd, for example, so x to the n would be like x to the 5th, for example, then the negative 1 would be to an even power, so it'll be positive. And if you look here, these odd degreed terms are positive, so that's set up properly. So that's the same thing. So anyway, that's how you can manipulate that geometric series, right? The one that has any function that can be related to this geometric series convergence function, this 1 over 1 minus x, we can manipulate it and get a power series for it. By the way, I forgot the plus c on that last bit here. The natural log of 1 plus x, we've got this whole series here, but we do need to find c. Just make sure that that it is 0. It is in fact 0 here. You know that the natural log of 1 is 0. So if we plug in 0 for x, that should give us natural log of 1, which is 0. So if we plug in 0 for all the x's over here, every single one of those terms is going to go to 0, and we're going to be left with c. So we get c equals 0. And so then we can just get rid of the c. And here is our series for the natural log of 1 plus x. Okay? On the next video that I'm going to make, and I won't be able to do it right now, if I don't get to soon, if I don't get to it today, I'll get to it tomorrow morning, I hope. We'll get into how to make a power series, and ultimately they call them Taylor and Maclaurin series. We'll talk about the difference there too. How to make a power series out of lots of different function types. So we'll build that in the next video. But this is a good start. It's a little review of what we did. I would practice some of the problems from section 11. I think it's 11.9 that last assignment was from as part of this. So thanks, guys. We're going to work through this. If this is confusing, watch it again if it helps. If it's not helpful or if you have any criticisms, please, by all means, pass that along to me. Thank you.